Okay, so we've had a little bit of a request to go through rather briefly the stuff that we've covered to this point in the last couple of weeks. So let's have a look at it. We haven't covered a lot. We've done some tricky questions, but we haven't actually covered that much. So let's begin at the beginning. This is, one would assume, the best place. All right, so let's start, say, around about here. What did we meet so far? Well, we met the Suvat equations. There we go. So we met the Suvat equations, and they were a good way to... Oops, sorry, I'm just trying to get rid of this little pop-up that's appeared on my screen. Oh, that's annoying. That's gone. Oh, thankfully. Okay, so they were ways to calculate missing things, be it the initial velocity, final velocity, acceleration, displacement, or time. So, hence the name Suvat. And Suvat equations were given by those equations there. So that's the Suvat equations. We've got V equals U plus AT, S equals UT plus half AT squared, 2AS plus U squared equals V squared, and 2S equals U plus V times T. All right. Now, V is final velocity, U is initial velocity. S is displacement. A is acceleration. And T is time. There we are. So that represents a Suvat equation. How we approach those questions is when you get something that's asking for a missing thing, be it acceleration or time or displacement. What you do is you write down what you have. You write down what you want. And by the time you've done that, you need to have a list of 4 items. 3 that you have, 1 that you want. And then it's simply just a case of picking the one that has the 4 things, the 4 items. So if you want acceleration and you've got initial velocity, final velocity and time, it's this one. If you want displacement and you've got initial velocity and final velocity and time, then this wouldn't do it. This wouldn't do it. You're down here. 2 times the displacement equals initial velocity plus final velocity multiplied by time. So you then do it that way round. Now, the reason why I'm starting here when we're just talking about the last couple of weeks is because, of course, when we're dealing with F equals ma and using F equals ma, then a lot of times it ties back into a Suvat equation to do a calculation. Okay, so you need to be comfortable with the Suvat equations. You need to be able to use them. You need to be happy using them. Now, thankfully, I've given you an awful lot of practice questions available in terms of that course that we've got online that you can go on there. Practice till your heart's content. By the time you're done, there should be nothing on there that you cannot do, if that's what you choose to do. There's a lot of information on there and a lot of practice. And pretty much everything on there, if memory serves, has answers associated with it. There is nothing on there that is lacking an answer. Okay, and that's on the Udemy course. So if you're not sure about using Suvat equations, get busy. Yeah, there's plenty of practice out there. Yeah, plenty of practice that I've given you that has answers associated with it. There's no reason in the world that you should not be comfortable or getting comfortable using Suvat equations. So, just to be clear on that. And that brings us down to Newton's laws. We met Newton's first. which was, oh, there's a whole bunch of ways you could say it, really, isn't there? In the absence of an external force, an object in motion will remain in constant motion or with constant velocity. An object at rest will stay at rest. That's one way to say it. You could say in the absence of an external force, the velocity of an object remains unchanged. Both of those work. We got Newton's second law. Let's put this: in absence of external force, velocity of an object is unchanged. Now, that's probably as small as we can make that definition there. Okay, so then we get Newton's second law. And Newton's second law is that the acceleration of an object is proportional to its force and inversely proportional to the mass of the object. So, acceleration is proportional to force acting on object and the acceleration is inversely proportional to the mass of the object. And we can write those things mathematically because they're mathematical words. So acceleration, this is actually the symbol for proportional. There we go. Acceleration, funky fish sign, to the force. Nice. Acceleration is also proportional. Oh dear me. Yeah, here we go. No, I did do it right. Inversely proportional. That's better. To the mass of the object. There we go. Oh, I was worried for a second there. So acceleration is proportional to the force. Acceleration is inversely proportional to the mass of the object. And you can combine those two. Proportional to this, proportional to that. You know what? Actually, it equals F over m. And from that, you can get the equation. Force equals mass times acceleration. You just rearrange this equation here. Okay. Now, this works for constant mass objects. And where have we gone from this? We started off, we got F equals ma. We got, oh, look, here's a brick. It's got a mass of 1 kilogram. It's got a force of 10 newtons. What's the acceleration? Straightforward questions. Yeah, and at that point, of course, it would be just 1 times 10, and that would give us, 10 over 1. 10 newtons of force acting on it divided by the mass of 1 kilogram gives the acceleration, which would still be 10 meters per second. There we go. 10 meters per second squared. We move from there to more complicated situations. So we go from this idea, I've got, say, a 1 kilogram object with a force of 10 newtons. Finding the acceleration, well, the acceleration is force over mass, which is 10 newtons over 1 kilogram, just as we talked about a second ago, 10 meters per second squared. We go from that to the situation, well, hey, okay, suppose I've got, you know what, a 1 kilogram mass here, and that's attached to another 1 kilogram mass here. And I've got a force of 10 newtons acting on it. Well, what's the acceleration? Well, the acceleration acts, of course, we get 10 newtons, but it's divided by the total mass, because you can't accelerate one without the other. So that's 1 kilogram plus 1 kilogram, and that's 5 meters per second squared. And then we get to ask the question, well, okay, what about the tension? So we've got tension in it here. I've got a tension of 10 newtons. T is 10 newtons. This first part here, but what about here? Well, I've got tension here, but what is it? And we have to look at, okay, we know the acceleration that that block is undergoing. And if we know the acceleration, we can calculate the force required to get that acceleration. So we get the force, which in this case is equal to mass times acceleration. the acceleration is 5 meters per second. The mass is 1 kilogram. 5 meters per second squared. That gives us 5 newtons. Okay, so we can look at that and say, hey, you know what? The force is being split between them. The tension here is 5 newtons. Total tension at the start would be 10 newtons. Tension here is 5 newtons. That's N looks like a 5 newtons in this section here. So force is being split between them. The total force moving this object here comes entirely from the tension. Okay, but what about situations where we've got an amount of force? Maybe we get friction acting in another direction. Well, okay, here we go. Suppose at this point I've got one block pulling this way with a force of 20 newtons. We've got a mass of 3 kilograms, and this way I have a force which is equal to the friction, and that's given by, I'd say, 11 newtons. Okay, so what can we do with this? Well, let's look at it. Let's look at it a little bit carefully. What do we have? We've got a force this way and a force this way. 20 newtons and 11 newtons. Well, because force is a vector, one of these is positive, one of them is negative. So I've got a resultant force, or a net force. It doesn't really matter which one you call it. Yeah, pick one. If you got a favourite, go with your favourite. Don't feel bad. You're not discriminating against the other one. Call it the resultant force, call it the net force. What? Let's just call it the resultant force. Why not? I prefer the resultant force. Makes me happy. There we go. Made the choice for you. Call it the resultant force. And the resultant force is just given by 20 newtons minus 11 newtons, which is 9 newtons, and that's 9 newtons in this direction there. So if we treat this as positive and this as negative, it's positive 9 newtons. Okay, which brings us almost to our last part. The last part is to find the acceleration of our block. The acceleration is force divided by mass. Here I've got 9 newtons divided by 3 kilograms, which is 3 meters per second squared. So we end up with those following pieces of information. And they go like this. Find total mass that will be accelerated. Find resultant force. We can use that to calculate acceleration. There we go. Or if you have the acceleration and the total mass, you can find the resultant force. If you have the acceleration and the resultant force, you can find the total mass. All right. So that was a little bit of a brief review, a brief jump over. While we're here though, what I want to do is introduce one final concept, which is Newton's third law. And it goes like this. For every action, there is an equal and opposite reaction. What does that mean? It means when you stand on the ground, your weight pushes down. You've got the weight, so I'll draw you a kind of a circle here. You've got the weight pushing down. But there's another force that has to balance this force. Why? Because if you've got a resultant force, you accelerate. So there has to be a force that stops that happening. So the net force, the resultant force acting on you is zero. That's why you don't accelerate into the ground unless it's muddy. In fact, that resultant force in this case is called, here we go, the reaction force. It's actually called the normal reaction force. Normal is a mathematical word here. It means at 90 degrees. So you've got the normal reaction force pushing up. So your weight pushes in the ground. The fact the ground doesn't want to move out the way it's pretty solid means that the ground pushes back. and that means that the total resultant force acting on you is zero. So here, in this situation, when you're standing on the ground, the normal reaction force is equal to the weight of the object. And that's why the object doesn't move down and it doesn't fly off into space. Okay, and that's Newton's third law. For every action, there's an equal and opposite reaction. For every action force, there's an equal and opposite reaction. If you push against a wall, you can feel the wall in your hand because the wall's pushing back. It just may not seem like it's not a conscious act on the part of the wall. But a lot of these things happen because what you're really dealing with is, here we go, for just draw a selection of things there. Just drawing a bunch of little springs holding some atoms together, because that's a bit like what it's like. The atoms have got this sweet spot that they kind of hang around on. So this is what matter looks like. A whole bunch of chemical bonds holding things at just the perfect distance. So it's difficult to imagine something like a wall pushing back, but how about a spring? You push down on a spring, the springs start to move. This one gets compressed here, these ones get stretched. There we go, maybe these ones start getting stretched as well. This one gets compressed, and of course it's going to push back. So you can see on an atomic level why that makes sense. But that's what I mean when I say it's not a conscious action. A wall will not consciously push back because it's a wall. It does not have consciousness. It does have wallness, but that's not as much of a measurable quantity. Okay, so there we go. That is Newton's third law. That is why it exists, and that is how it works at its most basic level. For every action is an equal and opposite reaction. Now you've already met this as an idea. How? Well, here we go. You remember this pulley? You've got two masses, M1, M2. Well, there's a tension in the string here. And that value of tension is the same here. If you've got two things that are attached, the amount of force, the tension pulling it in this direction is the same as the tension pulling it in that direction for an object that's moving. If this object pulls with a force of 3 newtons because it's accelerating, then this object is pulled with a force of 3 newtons. So both objects 3 newtons at this point here, the point where you have the tension in the strain, or the tension in the spring, or the tension in the connector, whatever it is, both objects feel that 3 Newton force. And that 3 Newton force travels from one to the other. One of them, it's pulled in this direction, one of them, it's pulled in this direction. You have your equal and opposite reactions, so they're both being pulled with the same amount of force. There we go. All right, hopefully that helped. We've now introduced Newton's third law. We're going to talk a little bit about that in a few minutes. Okay. In which case, I hope you guys have a wonderful day, and I'll be speaking to you very shortly.